the first video going over the 9-week review. Remember, the 9-week review is all of Unit 1. So we've covered Unit 1, Part 1, and Unit 1, Part 2. We've gone over the Part 1 test, and then on Tuesday we'll be going over the Part 2 test. So you'll have gone over and corrected both of those, plus done this review. And then I've listed here at the top of the review other ways that you could be studying. Your 9 weeks test is next Wednesday. So you've still got almost a week because you've got the weekend as well. So you can look at your notes, go through all of your notes that we've taken from day 1 in class. You can go to past assignments, especially the ones in Delta Math. You can go to those even if you've completed them or they're past due and you can't get credit. You can still go work problems. It'll keep generating new problems for you to practice. You can look over your past quizzes. We've had 4 quizzes that you can look at those. If you haven't corrected those, I encourage you to do that. And then of course the tests, which we went over Part 1 already together, and we'll be going over Part 2. And then of course this review, and this review is a grade. So in red here, I've just kind of listed out, this was Part 1 of the test. It's parent functions, transformations, key features of graphs. And key features includes domain range, increasing, decreasing intervals, intercepts, extrema, that's your maximums and minimums, symmetry, and end behavior. And then that was that part of the, also included inverse functions and composition functions. And then the Part 2 included what's in blue here, which was piecewise functions, continuity, and limits. Okay, so we're going to go through, I'm going to try and do this in 2 videos and do like everything in red in one video and then everything in blue, but we'll see how long it gets. It's a little bit longer of a review because it is more material. All right, so starting off with domain and range, we kind of reviewed this when we were going over the test corrections for Part 1. Remember that your domain are your X values and range is your Y values. Okay, so when we look at this first graph in number 1, we can see that it goes left forever, goes right forever, but there's a break. This is an asymptote here. Okay, we have a rational function. It does not exist. It is undefined at this X value of 4. So the graph is everything. It's everything except for 4. So remember in interval notation, that would look like this. It would be from negative infinity to 4. And we use parentheses on infinity and negative infinity because you never reach them. And then it would be a parenthesis for 4 because 4 is not included. It's an asymptote. We'd have a union and then a second interval from 4 to positive infinity. Okay, so we've got this first interval and then this second interval. So that's your domain. This means it's everything except for 4. And then the range is how low to how high the graph goes, which again is negative to positive infinity. But there's also a horizontal asymptote here. We can see that these graphs are approaching left and right. So that Y value of that asymptote is at 3. So that is a break in the range. So the range is everything except for 3. So there's your domain and range of that one. So for graph 2, this one is a square root function. It's been reflected down. So left to right, okay, this is not an arrow. This is an endpoint. So it does not go past this X value of -2, but then to the right, it goes right forever. And there's no breaks in between. It's continuous. So this domain would be from -2 to infinity, but the -2 this time is included. So we use a bracket. So there's a point there. And then the range, how low? Well, as it goes to the right, it's also going down. So it's going down forever. Okay, but again, this endpoint, the highest it ever gets, the Y value, is here at 5. So the range for this one, it's always least to greatest. Don't tell me 5 to infinity or 5 to negative infinity. It's least to greatest, bottom to top. So that's -infinity to 5. And again, the 5 would be included with a bracket. All right, now here is another domain question. This is just asking us to select all of the functions that have a domain of all real numbers. Negative infinity to positive infinity, that means all real numbers. So these are all the parent functions that you should know what they look like. You should just be able to picture this in your head. So I'm going to do some quick little sketches. Okay. I'm going to get a thinner line and give a little XY axis for each of these. And then I'll give you a quick little sketch in color. That might help organize it a little more. It's not asking you to do this. I'm doing this for the sake of reviewing. But you can look back at your parent function notes from, I want to say that was the very first day of school. The first week we talked about parent functions. Okay, so just y equals x or f of x equals x. This is just a linear function with a slope of 1 and a y-intercept of 0. So it goes through the origin with a slope of 1. So that's a line. Okay, this is the absolute value function, which is, oh, didn't get that very straight. The V shape that goes through the origin. This is the quadratic, which is the U shape. Okay, the square root function starts at the origin and shoots out to the right. The rational function is the one with those asymptotes, so it has two curves in the opposite quadrants like that. The cubic comes down, it's kind of the S shape-ish, where it curves through the origin like that. And the cube root, a similar shape, but goes more left and right than up and down. The exponential function has a horizontal asymptote here, and then it shoots up, increasing rapidly, exponentially. And then the log function has a vertical asymptote here, and it goes like this to the right. And then this is a constant. So this is just a horizontal line at whatever C is. So the way I drew it, that'd be like at -1 or something, just a constant. So they're asking which of these has the domain of all real numbers. Well, left and right forever, so that one does. As it goes down, it goes left. As it goes up, it goes right forever. So that one does. Same, that one does, that one does, does. Here, this does not. This does not have an arrow to the left. It has an endpoint. So this one does not have a domain of all real numbers. This domain would be 0 to infinity, including the 0. This one does not. Again, it has a vertical asymptote here. It doesn't go past 0. So this one does not have a domain of all real numbers. This one is 0 to infinity with a parenthesis on the 0 because the 0 is not included here. And then this domain is not all real numbers because of that vertical asymptote. This one is negative infinity to 0 union 0 to infinity. So this one's everything but 0. And then this one does, a constant does. So all but 3 of them have a domain of all real numbers as far as those parent functions go. All right, now increasing, decreasing intervals we talked about when we were going over this test are always the x values, okay? We're asking if the y value is increasing or decreasing, but the interval for our answer are the x values of that part of the graph. So when I read a graph, I read it left to right, just like I read a book. Okay, so I'm going to start on the leftmost and I'm going to trace this. So I am decreasing, decreasing, decreasing until I get to here and I change direction. Okay, and then I am increasing, increasing, increasing till I get to here. And then I'm decreasing, decreasing, still decreasing, little curve, still decreasing. Then I change direction here and I start increasing again. Okay, I'm going to do this in a different color. So the interval, you're using x values. So for increasing interval, that is the purple one. Oh, nope. Take that back. I did decreasing in purple, and I did increasing in the blue. Let's keep our colors straight. Okay, I'm going to give the X values for those. So for purple, the X value where I started, this was an arrow. So this is actually negative infinity. And then we stopped and changed direction here at this X value of -4. And then we turned purple again here at -1. And we're decreasing until we get to here at the X value of 6. And then in between those, I'm increasing. So here, this X value of -4 is where I started increasing until I got to this X value of -1. And then I increased again from the 6, and then that is to infinity because that's got an arrow on the end as well. So I would say I am increasing from -4 to -1, always parentheses, never brackets, and from +6 to infinity. And that I am decreasing from -infinity to -4, and from -1 to 6. Okay, so it's these X values that I'm highlighting. That's what the intervals are. So let's try that again. So this graph it's an arrow. So it's coming from -infinity on the left, and it's decreasing until I get to here. This is where I change direction. Okay, so there's a change in behavior of the graph, and I'm increasing till I get to this point. And then I am decreasing again, change direction, and increase again. So let me get my little highlighter. So the blue section, that X value is here to here, here, and that's the arrow to infinity. And then the purple was going left forever, so that's the arrow to here. That's the X value where it changed direction. Okay, and then here to here. So this one I would say is increasing. The first blue section, that's from -5 to -2. And then the second blue section is from 3 to infinity. And then decreasing, this is -infinity to -5. And then that is -2 to 3. Those are increasing and decreasing intervals. We used X values for our answers. All right, extrema and zeros. So remember zeros, that is your x-intercepts. It's where your graph crosses the x-axis. So in this case, that would be A, C, E, G, and I. Okay, and then extrema, remember extrema are maximums and minimums. So I'm going to use two colors. I'm going to use green for max. Oh, I should have used red for minimum. I guess I'll use a different color since I already used red. We'll use orange. Max and min, that's extrema. So looking at this graph, it's a maximum is any point where your graph, a relative maximum is any point your graph changes direction from increasing to decreasing. So B is a maximum. It is a relative maximum. As relative to the points on either side of it, it's a high point. It's a maximum point. Okay. Same concept for minimum. So I'm decreasing, 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 and then at point D, I change direction. I start increasing again. So this is a low point in the valley. So this is a relative minimum. Now, What is the difference in relative and absolute? Why am I saying relative maximum, relative minimum? Because if we look anywhere else on the graph, does the graph ever get higher and lower, higher or lower than these points? So for the maximum, I look across, over here it's getting higher. This actually goes up forever. That means that this has no absolute maximum. Okay, so all of the maximums or high points that you see, which I see another one here at F, all of these maximums are relative because there is no absolute, because these are not absolutely the highest points on the graph. The graph goes up forever, so it gets higher and higher and higher. So another relative max here. Okay, same idea for minimums. This graph goes down forever, so there is no absolute minimum. So all of these minimum values that we see, so H is another minimum, that one must also be relative. Okay, so looking at 7, arrows go down forever on both ends. So that means that there is no absolute minimum, but there is no arrow going up forever. So that means there must be an absolute maximum somewhere on the top of this graph. So the highest point on this graph is E. So that is my absolute maximum. It is absolutely the highest the graph ever gets. Now there's another peak, another high point, another maximum, but it's not the highest. E is higher than B. So E is absolute and B is relative maximum. Okay, and then we do have a low point, D, but again, this graph goes down forever, so there is no absolute minimums. This would just be a relative minimum. On this graph, this one's a little different. There's no arrows on any end. So the only change in behaviors I see a low point here where it changes direction from decreasing to increasing. And I see a high point here where it changes from increasing to decreasing. But for this high point, it's higher over here. So this is still just a relative maximum. But for the orange one, nowhere else, there's not an arrow here. It doesn't keep coming down. It stops there. So this is the lowest. So it is absolutely the lowest point on the graph. So it's the absolute minimum. Okay, now I look over here, and this is a high point. It is not a change in behavior, like it's decreasing on the right side of this point, but on the left, nothing exists. Like the graph starts here. So it's not a change in behavior, but it is absolutely the highest point on this graph. So even though it's not like a peak of a mountain like these other ones where it was two segments change or 2 points or two sides changing direction, that's still the absolute maximum. All right. Here we are stating the type of function describing the transformation. Okay, so again, we have to recognize what parent functions there are. So this has this x under the square root. So the square root of x is the parent function. So this is the square root function. Okay, now let's talk about what's happened to it. Okay, we need to remember that multiplying by a negative on the outside is going to reflect the graph over the x. So reflect over the x-axis because of that negative. We talked about when we were doing the test corrections that anything outside the function is affecting the graph vertically. So it's affecting the y values. So if you're changing to flip your graph over the x, you're changing it vertically. You're changing the y values. Now that 4 is outside the function. When I say outside for a square root, it means not under the radical. So this 4 is being multiplied on the outside. So this is vertically stretching the graph by 4. So it's going to get 4 times taller. And then that 3 is on the outside as well. It is being added or subtracted. When you add or subtract on the outside, remember that's your k. and that is your vertical shift. So this is being shifted down 3. And then, of course, you've got this add or subtract on the inside, this +2. Anything on the inside of the function is affecting it horizontally. Adding and subtracting is a shift. So this is shifting it left or right 2. And we need to remember that inside the function is the opposite. So that one is actually left 2. So I'll put a little reminder up here above this section that whatever function you have, I'm just going to call it f of x. Okay, what you multiply by on the outside we refer to as your a, and that a can be positive or negative. Okay, if it's positive, no reflection. If it's negative, it's a reflection over the x. And then whatever a is, that's your stretch. So if a is greater than 1, your graph is getting taller. It's vertically stretching. It's like you put your hands on top and bottom and pulled it apart. But if a is a fractional value like 1/2 or 1/3, it's between 0 and 1, you're actually compressing your graph. It's like you have your hands on top and bottom and you're squishing them together. Okay, so this is the vertical stretch or compression. And then you have minus h, that's the number added or subtracted inside, but the standard format of the equation is a minus, so that's why it's always the opposite of what you think. Because this being +2 means it was actually minus -2, so the fact that h was -2, that's why it was left 2. And then on the outside you have your plus k, that's your vertical shift. So it's up if it's plus, down if it's minus. All right, so then the second one here, I see absolute value bars. So absolute value of x is the function. And what's happened to it is, let's see, we've got an a value on the outside being multiplied. We said that's 1/2. We said that's going to be your vertical stretch or compression. And the fact that it's fractional means it's a vertical compression. Now, compression means it's being divided. So if you're cutting something in half, you're dividing by 2. So it's a vertical compression by 2. And then you have -1 on the inside. So remember, it's minus h. So h is actually +1. So this is to the right 1. So then on the outside, you have got +5. So remember, that's your k. So that is up 5. So no reflection in this one because we didn't multiply by a negative. All right, and then on 11, we've got the parent function is x squared. So this is the quadratic function. And let's talk about what's happening to it. This one does have a negative on the outside. So this is, again, a reflect over the x-axis. And then there's no a, so there's no stretch or compression. It's an understood 1. But then we've got +4 on the inside, so that's actually going to be left 4. And then we've got the +1 on the outside, so that's going to be up 1. Okay. So this next transformation one is similar to one that was on the test that was one of the most missed questions and had on the original test actually been changed to count as a bonus question. But let's talk about this again. So here is f of x, the original function. So this is what we're starting with. Okay, and then something happens to it, and we get this new function, g of x. We are trying to figure out what happened to f of x to turn it in to g of x. But it says to write it g of x in terms of f of x. And so we did these corrections on the test. We said, okay, I'm going to write f of x, but I'm going to have to write what's the a, what's the h, what's the k. Okay, so I'm going to leave some space for those things. So on the original function here to this one, I think the most obvious thing that stands out is that it's been flipped over. So instead of having this point come up here, you can see it's pointing down here. This shape has been flipped upside down, which means it's flipped over the x-axis. So we said, let me go back up here, we can see these at the same time. We said here that flipping over the x-axis was a negative a value. It's a negative on the outside. So I know that I'm going to have a negative for the a value. Now let's see, is there an actual stretch? So if you measure the width of the graph, so this goes from -4 to 3, so that's 7 across. Okay, and then you measure this, it goes from -5 to 2, so that's also 7. So it hasn't been horizontally stretched or compressed. And then how tall it goes from 2 to, so it's 4, 2, 3, still 4. So this is no stretch. So there's no a number. It's still the understood 1. But once this was reflected, let's look at where this would have lined up. So if that high point there is at 1, 2, and I reflected it, it would have ended up at 1, -2. And this point would have ended up at 3, -1. And then this point would have been at -1, +2. And then this point would have been at -4, +2. So this is like where that graph, what it would have looked like if it was simply reflected over, just flipped over. Oh, and that's not at 2, that's at 3. That looked a little steep there. That's at 3, 1. So it would be at 3, -1 there. There we go. All right, so we can see that one there is where it would be just with the flip, but it's not here, it's down here. So now we can see there's also been some sort of shift. So obviously we can measure like this end to this end, or this corner to this corner, or this corner to this corner, or this end to this end. It doesn't matter. I'm just gonna pick points to check from. So if it's easiest for you, it doesn't matter, pick one. So I'm going to pick these. So this has obviously gone down 1, 2, 3. So it's gone down 3, which means my K on the outside is -3. And then it has gone over, let's see, we went straight down 3. So then this has gone to the left 1, which means this on the inside would be +1. That would be my H, would be -1. So minus -1 comes out to +1. So that would be g of x in terms of f of x with what transformations had taken place from the original function. All right, now symmetry. We also talked about this in the test corrections. Remember, we are focusing on if the graph has x-axis, y-axis, or origin symmetry, or none of those. Okay, it can be none of those. Okay, so x and y-axis symmetry are line symmetry. It's like if I fold it on one of those axes, does everything align? Okay, so for this number 13, if I were to fold this over the y-axis, is there a point up here that would be mirrored over here, and there's not? Okay, what about if I were to reflect it over the, or fold it over the x-axis? And there's not a point that lines up that they would align. Okay, so this doesn't have any line symmetry. Origin symmetry is the one that's rotational, saying if you rotate it about the origin, so you were like to put your pencil down here on the origin to hold it down flat, and then you turn your paper 180 degrees, so upside down, does it look exactly the same as when it started? And this one actually would. Okay, so this one has origin symmetry, which if you remember, if it's symmetric about the origin, that means that it is an odd function. So this one has origin symmetry, so it's odd. Now, number 14 does have one of those line symmetries. If I were to fold this over the y-axis, all of these points on the left and right would match up. Okay, so this one has y-axis symmetry, which that's the one you need if your function is even. Okay, and then on 15, you can see here's the origin. If I rotated it about the origin, no symmetry. Folding over the y, no. Folding over the x, no. So this one has none of those. It's not reflected over the x, y, or origin. Okay, so of course it must be neither odd nor even. Now, if it had x-axis symmetry, it would still be neither odd nor even. Okay, so just y-axis is even, origin is odd. Those, you have to remember that those go together. All right, inverse functions. So inverse functions, you are switching x and y to start. So inverse means switch x and y. So remember, f of x means the same thing as y. So if it helps you rewrite that as y equals, great. And then we're going to rewrite it, switching the x there and the y here. And then we solve for y. So we want to do working backward. So remember, we're working backward from Pemdas because we're not evaluating. We're working backward to isolate a variable. Okay, so to do that, I'm going to first move this -1 over, and you move the terms by doing opposite operation. So then I've got x plus 1 equals negative square root of y plus 2. Okay, so then you want to get rid of the coefficient that's being multiplied there. So that's the negative. So I divide by an that's an understood -1. So I'm going to get rid of that negative by dividing it over. Now again, I don't need to leave 1 in the denominator. I just need to understand that this is going to change the sign of everything. Okay, so this becomes negative x minus 1. And then I'm left with that y plus 2 that I need to still get rid of. So I'm going to subtract 2. Now over here I have a constant and a constant, so I can actually combine those. So this one comes out to negative x, and then that would be minus 3. And that is y, and I'm going to indicate that it's the inverse with the -1. So that's the inverse of y, or the inverse of f of x. That is not right. I just realized I skipped a step here. When I wrote this here, I did not write the square root. So it's not just y plus 2, it's the square root of y plus 2. So we do need to get rid of that square root first. So the opposite of square root is to square. And what you do to one side, you do to the other. So I'm going to square it. And over here, it gets rid of the square root. Now I've got just y plus 2. So now it's time to subtract that 2. But when I do that now, because this -1 is in parentheses squared, I cannot combine those. So those have to stay separate. So I end up having negative x minus 1 squared, and then minus 2 on the outside. And that is my inverse function. So it's a quadratic that has been shifted down 2. And because this negative in here, this makes that harder for y'all to understand, but that's actually, if you factored out the negative, then that'd be +1, so it's left 1, but the negative on the inside reflects it over the y-axis. Okay, if you were asked to describe those transformations. All right, so again, pretend f of x is y, if that helps you. Then we're going to switch. So this would be x equals 1/4 y cubed plus 5. Okay, so working through it, I'm going to subtract the 5 first. So I've got x minus 5 equals 1/4 y cubed. Now I want to get rid of that 4. Well, or that 1/4, excuse me. I'm going to do it by multiplying by 4. Because if I multiply by the reciprocal of this, instead of dividing by a fraction, it makes it a little easier. And you can see that the times 4 in the numerator and the 4 in the denominator reduce, and it gets rid of it. But what you do to one side, you do to the whole other side. So that whole other side in parentheses gets multiplied by 4. So I've got 4 times x minus 5 equals y cubed. And then I need to get rid of the cube. So the opposite of that is to cube root. So then that's what I end up with. I have the cube root of 4 times x minus 5 equals y, and I indicate that that's the inverse with a little -1. And last but not least, now we've got a linear function. Remember, this is the same thing as y. So we switch x and y. Then this one's going to be the easiest to solve. You add the 1 over, so we've got x plus 1, and then you divide out the 3. What you do to one side, you do to the other. So the whole other side gets divided by 3. So this may be left as x plus 1 over 3, or it could be written, this is an understood 1 in front of the x, so it could be written as 1/3 x plus 1/3, where you separately divide those by 3 instead of having it all together over 3. So those are inverses. Now, inverses from graphs and tables, I think are easier, but you have to understand the inverse relationship, that the x and the y switch. So if it's helpful to you, actually physically switch them. So make yourself a new table for the inverse if you think it will help you. So instead of x and f of x, with x and inverse of f of x. So remember, what was the x column becomes the y column. What was the y column becomes the x column, because x and y switched. So all these coordinates that were the ordered pairs, there was a point at 8, 0. On the inverse, there's a point at 0, 8. So now that if you actually have them switched in the table, sometimes that's easier for you to evaluate. So this says to evaluate inverse of f of 0. So on the inverse table, because that's what I'm looking at, when the input is 0, the inverse table, when the input is 0, so that's here. So the output is the 8. Mistake a lot of people make is they want to say, oh, I'll just look on this table where it's 0. Oh, it's 1. No, that's on the original. When you input a 0, you get a 1. But on the inverse, when you input a 0, you get an 8 because these were switched around. Okay, you don't have to have made a table. You could just understand that if it's the input of the original, that means it's the output of the, or excuse me, the input of the inverse, it's the output of the original. So if you're looking for the inverse f of 0, you could say, oh, I need to look for where y is 0 on the original, and you can see it here. If when y was 0, x was 8. So that's on the inverse, when x is 0, y is 8. All right, now from a graph, it's the same concept. This is the graph of the original f of x. We're evaluating the inverse. So again, if it helps you write the coordinates. So they're looking for when x is 7, what is y on the inverse? So on the original, that would mean what is x when y is 7? Because the x and y switch. So that's what we're asking ourselves. On the original function here, when y is 7, that's right here. Here's my point. X is -5. So on the original function, there's a point at -5, 7. So on the inverse, there's going to be a point at 7, -5. So we'll do the same thing here. So for the inverse f of -1, that means we're looking for this y value. But on the original, that means there was a point at what? -1. So we're looking for where y is -1, what is x? So when the y value is -1, that's here. So here's the point on your graph, and you are at -2. So on the inverse function, there would be a point at -1, -2, because on the parent function, there's a point at -2, -1. All right, we're getting there. All right, composition functions. So this is where you're inputting one function into another. Here we have f of x and g of x both defined for us. So 20 wants us to find f of g of x. So they want us to take the g of x function and put it inside the f function. So I'm taking this equation and I am plugging it in for x here, because f is the outer function. Okay, so I've got 3, and then I'm inputting that whole thing. The whole g of x equation is what's being input. So that replaces the x, and then I have -7. Okay, so you can see the g of x function is input inside the f function. Okay, if it helps to see it this way, like with 2 colors, the g is actually inside the f. So this is the f function, this is the g function, and I'm putting the f inside there as the input. Okay, now I need to simplify. So nothing to do inside, so I can distribute. So I've got -3x squared, and then that would be +6. Then I've got the -7. I can combine like terms, both constants. So this is -3x squared minus 1. Okay, now 23 has reversed this. They've put f as the inner function and g as the outer function. So I'm plugging f into g this time. So I'm taking this entire equation and plugging it in just right there. So g is going to be the outer function. So I'm going to have negative parentheses square plus 2. That's the g. And then on the inside, I'm going to plug in 3x minus 7. So that is the f function on the inside. So then I need to simplify. This one's going to be a little more complicated because you have a binomial 2-term expression being squared. So that means I'm actually doing 3x minus 7 times itself. And all of that has to be done first, order of operation wise. And then there'll be a negative outside there that'll get distributed, and then there'll be a +2 that gets combined. So the foiling of the squaring the binomial, remember that's first times first, and then outer, so negative, the -7 and the 3x would be -21x, and then inner, -21x again, and then last times last. So -7 times -7 would be +49. Now remember, all of that has to have that negative distributed and then the 2 added. So distribute the negative first, so all the signs change. I'm going to go ahead and combine these. That would have been -42, but I'm distributing the negatives. It's going to be +42x, then -49. And then +2. Then I can combine those like terms. So I've got -9x squared plus 42x minus 47. And that is your g of f of x. Then last but not least, now they have an actual number. So they have f. Oops, thought I had my highlighter chosen. So they have the f function inside the g function, just like the last question. F is inside g, but inside that then is a number. Okay, so we're going to work inside out. So I'm going to say, okay, I'm going to find this f of 2. So I'm going to take the f function and I'm going to input a 2. So 3 times 2 minus 7. That's 6 minus 7 is -1. So f of 2, this right here, is -1. So I'm going to replace that. I'm just going to say, okay, what is g of -1? So I'm going to go to the g function and I'm going to input that -1 because f of 2 came out. I get a different color here. F of 2 came out to be -1. So that got plugged in there because that's the input. So -1 squared is +1, but then you've still got this negative outside. And then that +2, so that comes out to just 1. Oh boy. Yeah, I think this is the last 2 for this Unit 1, Part 1. So we'll do these last 2, and then this video will end, and then there'll be a second video for the Part 2 of Unit 1. Okay, so this one is asking for end behavior. So remember, end behavior is the left and right-hand sides of your graph. What are they doing? Okay, so I would say this left side is rising. Okay, so the left side's going up, and the right side is going down. But we have a special notation for end behavior, and you need to remember the left, we're talking left and right, so we are looking at the x-axis. So as the x-axis goes left, that's actually going toward -infinity, if this is going forever left, which it is. Okay, and to the right is +infinity. Okay, so left-hand end behavior, we would say as x approaches -infinity, that little expression right there, that means left. And then to say that it's rising, it's going, the y value is going up, I say f of x approaches infinity, so positive. So as x goes to the left to -infinity, y, or f of x, is going up to +infinity. That means the left side is going up. So here, for the right end behavior, right side is where x is going to +infinity. So this means right. So as x goes to +infinity, f of x, or y, in this case is going down, so it's going to -infinity. So this means the right side is going down. So what's in purple is the notation that you need. For 26, I could say the left side. Now this one is a constant. Okay, there's not an asymptote here. This just happens to be a constant function piece. So I would say as x is going to the left, so as x goes to -infinity, f of x is not going up to positive or down to negative. It is staying at a constant rate at this y value of -3. So as x goes to -infinity, f of x goes to -3. It doesn't move, it's staying constant there. Okay, and then on the right side, this is not an arrow. This graph stops here. So the right end of this graph is not as x approaches infinity, it's as x approaches and whatever the x value is there, in this case, 6. So the right side is x approaches 6 instead of x approaches infinity because there's an endpoint instead of an arrow. So as x is moving toward 6, the y value is moving toward, this right here is -6. And that's and behavior. All right, I'm going to stop that video there. You can watch the second video if you need help with the rest of the review.